Good morning. Bonjour. Mela, konħattaw. Alright. Mela, irċivejtu hu l-messaċ il-bira. Battilkom messaċ. Ħubdu paċenza, zittilkom domanda f'dak il-homework, alright? Naf li ġitwi, naf. Imma għax għandi ċaġa f'moħħi ta' għalek. Ħubdu paċenzja, namluħ kif tajtkom ta' Mela, ovvjament, jekk ikolkom problemi importanti tkellmuni. Alright, tħallux, toqgħodu xtabġu fil-vojt. Aqbdu għajdu li mill-ewwel. Mela, ħankomplu daqsxejn fejn ħallejna l-aħħar darba. Mela. Alright. Mela l-aħħar darba il-bieraħ dejna nitkellmu fuq graphs, fuq displacement time graphs. And for now, what we said was that we have to read the graph, alright? We have to read the graph to be able to understand where the object is and what the object is doing. And for now, we looked at two graphs. This graph, where actually at 0 seconds it was at 20 meters to the right of the reference point, and it remained at 20 meters to the right of the reference point. And in the second graph, where at 0 seconds it was at the reference point because the displacement was 0, but as time went by, the displacement started to increase until at 40 seconds the displacement was 20 to the right. Therefore, this means that the object is moving to the right. Now, from these graphs, alright, we can calculate the velocity. How? Because if we calculate the gradient, of the graph, għaw min jaf jgħid li xi tfisser gradient. What is the gradient? Isa, għandna liqli. Very good. The gradient it's a mathematical idea sewa. Bil-mathematics, gradient is the slope of the graph. Is how steep the graph is. Very good. And it is calculated by finding the change in y over the change in x. Ux vera? Change in y over the change in x. Li, in reality, we can do those changes, we can calculate those changes by making y2 minus y1 over x2 minus x1, where y2 and y1 and x2 are the coordinates that you're going to take. So you're going to take 2 points. You can take 2 points wherever you want to. Write down the coordinates. So this is x1, y1, and this is x2, y2. Alright? And then use them in this formula. When you're calculating y2 minus y1, you're finding this distance. Dik tiġi y2 minus y1. Għax tiġi difference. That's why it's called the change in y. Change in y. Alright? And this is the change in x. That's x2 minus x1. That is the change in x. That's why you find the slope when you find the gradient, because you're dividing how much you have height all over how much the slope is moving, is spanning in the x direction. Therefore, you are calculating the slope. Although gradients are practically mathematical tools, as usual in physics, we use those mathematical tools to find something in reality. And in physics, each and every gradient represents something. Alright? Aħna fil-physics ma nużawx il-gradients biex nsibu slope tal-graf. X'insibu għamlu slope tal-graf? Il-slope tal-graf trid tirrappreżenta xi ħaġa. And in this case, the slope of the graph represents what? Look. The change in y, on the y-axis I have displacement, so change in y in our case is change in displacement. And time is on the x-axis, so the x-axis is change in time. But change in displacement over change in time is what? Isa. Velocity. Alright? Therefore, the gradient of this type of graph gives you the velocity. Alright? Issa, when you calculate the gradient, we're going to calculate the gradient using this method. You can choose the 2 points where you want to, but as you may already know, it's very important to take the points as far from each other as possible. The idea is such that if you make a mistake when reading the coordinates, if the coordinates are very close, that mistake is a very large percentage of your change in y and change in x. But if you take them very far away, the same mistake that you are taking will be a very small percentage of the change in y and change in x. Therefore, if you take a mistake when you are reading, a small mistake, if you take a small mistake when you are reading the coordinates, it will not affect so much the result. So take the points as far as possible from each other when calculating gradients. Now, another thing, the gradient, such the importanti ngħiduha, a gradient has a value of 0 when the line is how? Supposta fuq għadi naħseb isa. Meta jkun gradient 0? Tafu? Issa xi darba diskutajt. When it's horizontal. When the line is horizontal, the gradient is 0. If the line is vertical, in fact, having vertical lines is not so real. In reality, we don't have gradients in these types of graphs. Alright, qegħdin taraw nisew? Jew waqaft. Waqaftu. Hello. Mela, when you have a vertical line, alright, the gradient of a vertical line is infinity. Għalfej, għax ikollok change in y over 0. Anything divided by 0 will give you infinity. Infatti fuq il-calculator jekk tagħmluha tiġi error. Alright? So in reality, it's very difficult, it's almost impossible to have vertical gradients, alright, in these types of graphs. Now, so 0 is the minimum, infinity is the maximum, therefore, as the gradient gets steeper, alright, it increases in magnitude until its maximum when you have a vertical line. On the other side, it's still the same. It's 0 if it's horizontal and vertical infinity. But if it is inclined in this direction, then the gradients will be negative. If it's inclined in this direction, the gradients will be positive. Alright? So this is you need to know this, alright? So gradients inclined in that direction, they are positive, in that direction they are negative. As they get steeper, the magnitude gets larger. Alright? Tajjeb sawnek? Kulħadd alright? Issa. Alright, one last thing. For this type of gradient, this gradient which I have here, is the gradient of the graph changing or not in this case? Isa. Is the graph changing or not? Wejja, come on. Attenti. Isa. Il-line, the steepness of the graph, is the steepness changing or the steepness of the graph is always the same? It's the same because it's a straight line. Qegħdin niftehmu żgur? Qegħdin tifhmu. Billi hawnhekk il-gradient mhux qed jinbidel, the steepness of the graph is not changing, it's just a straight line, full stop. Therefore, what's happening here, it's that the gradient is not changing. Therefore, since the gradient represents the velocity, even the velocity is not changing. Qegħdin niftehmu. Therefore, I can say, because last time we stopped up to that point, ux vera? So we can say that the object is moving to the right at a constant velocity. So from the shape of the graph, you can identify if it's a constant velocity or not. At a constant velocity of, and we can calculate the gradient. Mela, ħanikkalkulaw. So gradient is y2 minus y1 over x2 minus x1. So mela ħanħassar ftit daw ħankun nista' nikteb il-propja. Issa Kif għattilkom, you can take points wherever you want to. I'm going to take this point this time, which is 0, 0, alright? And this point, the last one, which is 40, 20. Sound okay? 40, 20. Therefore, the gradient is 20 minus 0 over 40 minus 0. So in other words, it's 0.5 meters per second. Dux vera. Now, the result of the gradient is positive, obviously, because the gradient is positively. But what does it mean that the gradient, therefore, the velocity is positive? What does it mean that the velocity is positive, Isa? That the velocity is pointing where? To the right. And in fact, if I get back to my diagram here, it makes perfectly sense. Alright? It makes perfectly sense. Because the object is moving to the right, therefore the velocity should be positive. And in fact, the gradient is confirming that the object is moving to the right. Tajab sawnek? Alright? Now, the last type of graph that I'm going to discuss for these displacement time graphs is when you have a graph something like this. So if we have a graph, but this time the graph is a curve, okay? This time the graph is a curve. استنى تاش عملتها حزين. هيك هي. 10, 20, 30, 40, 50. Okay. So let's say I have this type of graph, displacement time graph. All right. Let's start interpreting it. So first I'm going to do exactly what we did yesterday. So first I'm going to read the initial point and the final point to understand exactly what's happening. So the first point, if we read the first point starts from 0, 0. So what I'm saying is that at 0 seconds, what does it mean, 0 displacement? أنا رأيك تفتكروش من البيرة. What does it mean, 0 displacement? ليه attent Matthew ليه qiegħed fil-reference point dik tfisser issa ħaniġi għal tiegħek Matthew għax di li għat li inti mhux ħafna jieħduh dak l-iżball. Mela, attenti, issa nispjegalkom. So, 0 displacement means that the displacement is 0. Issa displacement we measure it from the reference point. So if at 0 seconds we're at the reference point, it means that we are at the reference point. We don't have any displacement at the beginning, so we are there. Now, it does not mean that the object is at rest. It does not mean that the velocity is 0. Alright? Għaliex? Because the gradient of this graph shows us the velocity. Okay? It's not, the graph is a displacement time graph, it's not a velocity time graph. So what we are reading is just the displacement, not the velocity. To calculate and to check what's happening to the velocity, we have to find the gradient at that point. Qegħdin niftehmu, attenti. It does not mean that all the graphs start from 0 meters per second. If you are, for example, monitoring a race, all right? And you start your stopwatch when the athletes are exactly in front of you, they are not starting from 0 meters per second. Okay? Attenti, għax dan huwa żball komuni ħafna li jagħmlu studenti tal-età tagħkom. Attenti, il-graphs ma jfissirx bil-forsi jibdew dejjem minn 0. Alright, 0 meters per second. Għax inti tista' tibda tiċċekkja s-sitwazzjoni minn fejn trid. Okay? Mela. So this only means that the object started from the reference point. It's at this reference point at 0 seconds. At 50 seconds, alright, the displacement now is, inserta 50 u kollu, ġvera, is 50 as well, is 50. So at 50 seconds, the displacement is 50. It's a positive 50. So if it's a positive 50, what does it mean? That the displacement vector has a magnitude of 50 meters and it's pointing to the, where? To the right. So this is my displacement vector at 50 seconds. So the object is here at 50 seconds, 50 meters away from the reference point. Therefore, we can already say that the object has moved to the right in these 50 seconds. Taqblu miegħi? Because it was at the reference point and now it is 50 meters to the right of the reference point. So we can start writing the description of this part of the graph. So the object is moving to the right. Sound correct? Tayyeb is moving to the right. Now we know that the gradient of this graph gives us the velocity, ux vera? So look at the graph. Is the gradient of this graph in this case constant or is it changing? It's changing because it's not a straight line. The gradient is changing. So in this case, I can't say at a constant velocity of, because the velocity is not constant. Now, when you have a graph like this, you can't give the velocity because the velocity is changing all the time. This is one of those cases where we have a situation where the velocity changes continuously. As you can see, the gradient of the graph, the slope of the graph, is changing continuously. There are no 2 points where the slope of the graph is the same at Tarawa. Continuously it is changing. So I can't just find the gradient if I take the coordinates of this point and the coordinates of this point and calculate the gradient normally, y2 minus y1 over x2 minus x1, I would have found the gradient of that line, which doesn't have to do, which is not my curve at Tarawa. And this is why I told you that when you use the formula for velocity change in displacement over change in time, which is actually our gradient, you can't use this formula when the velocity is changing all the time, because if you use it, you will just find the average velocity. This is the reason. Now you can see why. Because if the velocity is changing all the time, as in this case, if you just use that formula, you would be finding the gradient of that line, which is not your curve. Tarawa, graphically tkun tsaw tarawa aħjar. Issa. But we said, when we were doing the theory, we said that there is a way how to find the velocity at a point, ux vera, and we wrote it like this, the s by dt instead of delta s by dt, by delta t. Alright? And in this case, I'm going to explain how we can find the velocity at a point in time. The velocity at a point in time. Mela, let me start by doing this. So, let's say that we want to find the velocity at this point. Alright? The velocity at this point. I want to find the velocity at this point. Now, if I find this gradient, can I say that that gradient is the gradient of the slope at this point? Let's say it's point x. At point x, u what dak il-gradient l-slope at that point? Attent, Matthew. Ara kif ħanipprova norijilkom. L-slope tal-graf edha hekk, le? Sanna. Edha hekk, taqblu miegħi. Imma l-line li għamilt jien qiegħed hekk. Qed tarawhom għandhom differenza l-slopes tagħhom. Ħanipprova nispjega ftit aħjar din. Jekk jien għandi curve hekk, okay? L-slope ħanamilhom bl-aħdar. At this point, the slope at this point is in that direction, taqblu miegħi. The slope at this point is in this direction, ux vera. The slope in this position is in this direction, and the slope in this position is in this direction. Taraw l-slope qed tinbidel il-ħin kollu. What I have drawn in this case is this, and this slope and this slope, they are completely different. Tarawhom, they will not give you the same value. So, in some way or another, when I write ds by dt, it means that I am going to try to find this slope which is touching the curve. Qegħdin niftehmu. Fimna hawnhekk? Mela. So, the red line that I've drawn here is not the slope of the graph at x, it's not. But if I decrease the change in y and change in x and get closer to that point, ara bħal pereżempju hekk, I'm getting closer, ux vera. The slope of this second line is not the slope of the graph, but I'm getting closer. Taqblu miegħi. If I change the color and the thickness, forsi taraw aħjar. If I get closer, so if I am decreasing the change in y and the change in x again, look, this is the change in y and change in x again, I'm getting more closer to the slope of the graph, alright? And if I continue on doing this method, getting closer, 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 at a certain point, if delta x and delta y, they are very, 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 very small, and that is what d represents, a very, very small change, I will get at that point, and therefore I will find the gradient at that point as required. So, alright, qegħdin tifhmuni s'issa. Now, to do this method, it's not a simple method, but to do this method, there is a method which is called calculus. Alright? And you will be doing this in mathematics. L-ewwel darba ħatoqgħodu tagħmluha hekk, imbagħad hemm metodu iktar faċli kif jirnexxielkom tagħmlu il-gradient at a point. Alright? U l-mod kif niktbuha huwa kif ktibta jien, ds by dt. Issa. But in physics, we're not going to use calculus, alright? For this level, for A level. Ġifieri min ħajkompli bachelor in science, jew min ħajkompli engineering, jew min ħajkompli architecture, jew whatever, u mbagħad iva, mbagħad tibdew tużaw il-calculus, ta' għaliex dak huwa l-metodu propja biex issib gradient at a point. Din mhux se nużawha f'dak topic biss, għalhekk qed nieħu daqsxejn ħin. Jiġifieri tużawha f'topics oħra wkoll. So, in physics, how are we going to find the gradient at a point if we're not going to use calculus, if we're not going to use this method? What we're going to do is, we're going to use a graphical method. It's not a perfect method, alright? It's not a perfect method, but we can still use this method to find the velocity at a point. How are we going to do this? What we're going to do is literally drawing the slope of the graph at that point. So if I want to find the velocity at point x, so it's the instantaneous velocity at point x, what I'm going to do is I'm going to draw a tangent. I'm going to draw a tangent. Now, you did something about tangents, ġvera, at O-level maths. The definition of a tangent is if I have a circle, okay, the tangent, if the tangent touching this point, is a line which is perpendicular to the radius. So xekk kontu tagħmlu. It's perpendicular to the radius. Now, in this case, it's a little bit more difficult because the curve is not a perfect circle, it's a curve. So, if you're going to draw a tangent, you have to draw a line, alright, using your ruler. So, take your ruler, m'għandix ir-ruler hawn, iva hawnhekk keda. So, take your ruler, this is the curve, take your ruler, and touch the ruler at the point where you need to find the instantaneous velocity, and move the ruler until it is balanced on the curve. Ġifieri, the amount of space between the tangent and the curve on one side should be approximately equal to the space on the other side between the tangent and the curve. So we have to balance the line on the curve. And when you balance the line on the curve, that would be your tangent. M'għamiltux sew. Ħaġek. Aħjar. Ivek aħjar. Alright? That will be... Le, għamiltu isqlilaw. This is the problem with this method. That's why... Senna ta' ma nistax nagħmlu mhux qed jirnexxieli. Ftit ieħor. Hekk, alright, hekk aħjar. Alright, so the tangent should be balanced, alright, on the curve. Now, you can draw the tangent as long as you want to, alright? You can draw the tangent as long as you want to. If you want to, you can draw a tangent. Ma nistax, mhux ħajrnexxieli. Correct. You can draw the tangent as long as you want to. Alright? It doesn't make any difference. Then, as soon as you find the tangent, so the tangent has a gradient which is equal to the gradient of the slope at that point. Then you just find the coordinates as usual. All right, so write the two coordinates. Man għandek x2 comma y2, you have x1 comma y1, and then find the gradient of the tangent. So we're going around this problem in physics to find the gradient at a point on a curve, therefore the instantaneous velocity at that point. What we're going to do is we're going to draw a tangent and then find the gradient of that tangent. It is very important that the tangent touches at just one point, at the point where you want to find the instantaneous velocity. As you can see, it's not a perfect method, all right, because it will vary from one person to another, because it depends on how you draw the tangent. Okay, and that's why we have a mathematical method, which is the calculus, which we're going to do in pure maths, to have an accurate method how to find the gradient at a point, because this is not an accurate method, it's just an approximate method. But although it's an approximate method, it can give you very good results. Just be sure to draw a good tangent. All right. One last thing about this method. Obviously, if you repeat the method at any other point on the curve, for example at this point, as you can see, the gradient will change. The gradient of the tangent will be different. Why? Because at a different position, the slope of the graph is different. Therefore, you will find a different velocity. Sound right? Sound okay? Yes. So let's continue to write this down. So the object is moving to the right. Now, it's not moving at constant velocity, vera. What is the velocity doing? If the gradient, look, the gradient was like that at the beginning, and then it is getting lower. So if the gradient is getting lower as time is passing by, what's happening to the velocity? Since the velocity is equal to the gradient, the velocity is, sorry, Maria, is decreasing. Therefore, the object is moving to the right and decreasing velocity. Okay, and decreasing velocity. You have to find the gradient at a point if you are asked to. All right, because you have to be asked to find the gradient at a point, and the point has to be marked. All right, if you don't have that, you don't need to find the gradient at a point, but at least we know that the gradient is decreasing, therefore the velocity is decreasing. Now, regarding what we said about the initial point, look at this in this case. If I draw the gradient at the very beginning at time 0, the curve is something like this. So the gradient is in that direction. Is that line that I've drawn right now, does it have a gradient 0? Yes. Does it have a gradient 0? No, it doesn't have a gradient 0. So in this case, this was a particular case where the problem started from a point where the velocity was not 0. In fact, the velocity is very large because it's steep, the gradient at the beginning, and then the gradient gets slower. So the velocity gets smaller. Alright, sawnek? Edin tifmuni? Kulħadd sew? Kulħadd alright? Okay, so that was our first type of graph, all right, a displacement time graph. Now, here I have all the information, all right, that I've just said. This is another graph that you can have, all right, the last one. It's still a graph where the velocity is changing all the time. In this case, is the velocity increasing or decreasing? What's happening to the gradient in this case? Increasing, because the gradient is getting steeper. All right, therefore in this case the velocity is increasing. Issa, mussa noqgħod naqra dil-informazzjoni hija dak kollu li għadna llum. All right, now I'm going to skip some pages. I will get back to them and move to page 6 issa. Morru kollha page 6. All right, page 6. Okay, now So in page 6 we have this graph, all right, and we're going to practice a little bit to interpret the different parts of the graph. Now, now this is a very complex graph, all right? Normally you're given smaller graphs, okay? But this is a graph that you can expect. So what we're going to do is we're going to use whatever we learned till now about displacement time graphs, and we're going to interpret each and every piece of the graph, all right? Each part of the graph. Wherever we have constant velocities, we can find the constant velocities right away, okay? Mela, okay, let's start. So let's start with the very beginning, okay? So we have A and B. So the first thing to do is to read what's happening at the two extremities of that section. So at the beginning we know that at A here, all right, at time 0 the displacement is how much, Isa? 0. So at the beginning we are at the reference point. So if I draw a diagram showing the positions of my object at the very beginning at A, the object is at the reference point. The object is at the reference point. The reference point is the point from where you are measuring all your displacements, all right? At B then, at B, the displacement at B is, what's the displacement at B? 10, all right? It's plus 10. So the displacement has to be drawn from the reference point to the right, and it's 10 meters. Ux vera? 10 meters. So now the object, my object, is at this position at B. So I can say that the object has been moving in which direction? Isa. To the right. So AB mela AB, I can say the object is moving to the right. Now, is it changing velocity or not? Is it at constant velocity or not? Isa. It's changing velocity because it's a curve. Now, how is the velocity changing? Let's draw some tangents. If I draw a tangent here, a tangent there, and then a tangent there, what's happening to the gradient of the tangent? Increasing. Therefore, I can say the object is moving to the right and increasing velocity. All right, Saunek? So that is my first part of the graph. All right, that's my first part of the graph. Let's continue. BC now. At B, we are 10 meters away from the reference point. At C, we are at 30 meters away from the reference point, and it's positive. So the displacement is positive. So the displacement is pointing to the right. Therefore, if I draw this displacement again, attenti, we draw the displacement always from the reference point, always from the reference point. All right, that's why the reference point is very important. So we are 30 meters away from the reference point. So now the object is at this position. All right, that is position C. So from B to C, the object continued on moving to the right. Ux vera? Continued on moving to the right. Therefore, I can say the object is moving to the right. All right. Now, between B and C, is the gradient changing or not? No, it's a straight line. Therefore, at a constant velocity of, and we can calculate now the velocity. When it is a constant velocity, we can calculate it right away. Aħdmu please. Isa, mela, ejja nagħmlu BC. Ħankabbar ftit nerġa'. So, first of all, let's write down the coordinates. So the coordinate of this, the coordinate of B għanna mela 10, 15, 10, and the coordinate of C is 20, 30. Okay? So if we calculate the gradient now, mela ħanikdbu hawnhekk. Il-gradient huwa mela għandna y2 minus y1 mela 30 minus 10 over 20 minus 15, u ġver? Ek. Mela għandna 20 over 5. Mela suppost jiġi 4 meters per second. 4 meters per second. Okay? Tajjeb? Issa. The gradient is positive or negative? Isa, it's obvious. Positive. So what does this, skużawni, what does this mean that the velocity is positive? It means that the velocity is pointing to the right. In fact, if I draw the velocity which is pointing 4 meters per second and it's pointing to the right, it makes perfectly sense. Taraw? It makes perfectly sense because the object is moving to the right, therefore the velocity should be pointing to the right. Okay, BC? Ħammorru CD issa. CD. At C, we are at 30 meters away from the reference point. At D, we are at 40 meters away from the reference point. So, again, the object now is at 40 meters away from the reference point. So, the object is at this position at D. Therefore, between C and D, the object is continuing on moving to the right. It's continuing on moving to the right. Therefore, the object is moving to the right now. Between C and D, it's a curve. So, are we moving at constant velocity or not? No? Eidli Maraya? Decreasing velocity, very good. If I try to draw some tangents, alright, at C the tangent is something like that, at X the tangent is like that, at D the tangent is like that. So the gradient is decreasing this time, the gradient is decreasing, therefore the velocity is decreasing. Mela jena ħanikteb, the object is moving to the right and decreasing velocity. Alright? It is an important thing to note that although the gradients are decreasing, alright, but all the gradients between C and D, they are positive. They are positive, which means that the velocity is decreasing, but all the velocities during this time, they are all pointing to the right because they are positive. And in fact, it makes sense because from this diagram, although the velocity is decreasing, it is decreasing, but the velocities are all pointing to the right because it's moving to the right. Taraw? Daw jiġu jigsaw puzzle ta' daw it-tip ta' domandi, ġifieri suppost kollox għandu jaqbel. Minn naħa jew minn oħra taraw minn fejn tarhom għandhom jaqbel. Jekk tara li hemm xi ħaġa mhux qed taqbel, sinjal li qed tinterpreta xi ħaġa ħażina. Okay, DE. DE issa, which is this part. Now, from D to E, at D we are at 40 meters away from the reference point. At E we are at 40 meters from the reference point. So what happened between D and E? Ma ċaqlaqx, proset. So from D to E, the object didn't move. It remained at the same position because it was at 40 meters and it remained at 40 meters. So in this case, I can say the object is at rest. Jew inkella tistgħu tużaw il-kelma wkoll stationary, both of them are correct. Għajdli? Imma stationary mhux meta jkun 0 meters per second. Imma din mhijiex graf ta' velocity time, din hija graf ta' displacement time. Ġifieri id-0 fuq dil-graf tfisser li qiegħed at the reference point. Okay? Infatti jiena ħafna drabi nsejt ngħidilkom, normalment inħobb kif nara li hija displacement time graph mill-ewwel nikteb gradient equals velocity. Ħalli intom sakemm tkunu qed taħdmu dejjem taħsbu. Meta tiġikom id-dubju fuq il-velocity jgħid imma x'inhu l-gradient. Alright? Tajjeb? Infatti jekk taraw il-gradient ta' DE jekk nipprova mpinġi huwa orizzontali. U gradient ta' line li huwa orizzontali kemm jiġi l-answer? Kemm hu l-gradient tiegħu? 0. Infatti il-velocity hija 0 meters per second. Wieqaf. Alright? Taraw? Fimna saw? Okay? Mela. So the object is at rest stationary. Alright? Jekk tgħidha hekk diġà biżżejjed, imma nistgħu ngħidu at 40 meters to the right of the reference point. Id-displacement time graph di li għandhom tajjeb ħafna li bid-displacement time graph tkun taf il-pożizzjoni tal-oġġett kull sekonda. Taf eżatt fejn qiegħed. Alright? Dik li hija tajjeb fid-displacement li m'għandniex pereżempju fid-distance, li bid-displacement you know exactly the position of the object at all times. Alright? Okay, ħan iddiskuti EF u niqfu għaw illum. Mela, EF issa. EF. At E we are 40 meters away from the reference point. At F we are at 35 meters away from the reference point. So if I draw the displacement now, which is 35 meters positive, so 35 meters to the right, f'dan id-diagram li qed nagħmel ħadd tiġi hekk. Nħassar daqsxejn di. Mela di kienet 40 meters. 35 meters from the reference point ħadd tiġi xi ħaġa hekk, hux vera. So, between E and F, now the object is at this position. Now the object is at that position. So what happened now? So at D and E, it was at 40 meters. It was at this position. But now at F, alright, at F, the object is at 35 meters to the right of the reference point. So between E and D, E and F, the object now moved to the left. Taraw kif tidu tinterpretawa. So I am interpreting first what's happening to the displacement. And from the displacement was 40, and now the displacement was 35. So actually the object moved closer to the reference point. It's coming back. Alright? So in this case, I'm going to say the object is moving to the left. Alright? Now, between E and F, is it moving to the left at a constant velocity or not? No, because it's a curve, which vera. Let's check what's happening to the gradient. So at E, the gradient is horizontal. At this position, the gradient is like that. And at F, the gradient is like this. So the gradient is getting steeper, which vera. The gradient is getting steeper, taqblu miegħi. But all the gradients are negative in this case, which vera. They are negative in this direction, it's negative, not positive. Għax positive meta jkun normali. Mela kontra jiġi negative. Ġifieri in this case, the gradients they are negative. All of them. But although they are negative, they are getting steeper. Ġifieri, per eżempju, hawnhekk kien 0, mbagħad -2, per eżempju, mbagħad -10. Now, these are velocities. The minus of a velocity means that it is pointing to the left. So what I'm saying here is that the velocity is pointing to the left as it should do, because we said that the object is moving to the left, which vera. But the magnitude of the velocity is what? Since the gradient is getting steeper, the magnitude is increasing or decreasing? Increasing. Attenti, għax tistgħu titħawdu. So I know that the gradients are all negative. That's because the velocity is pointing to the left. But the magnitude of the gradient is getting steeper, therefore it's getting larger. So the velocity is increasing. So here I can say the object is moving to the left, or right. In fact, the velocities are pointing to the left. And increasing velocity. You have to decide if it is increasing or decreasing velocity by checking what's happening to the magnitude of the graph. If it's getting steeper, it's increasing velocity. If it's getting lower, it's decreasing velocity. So in this case, it's increasing velocity because it's getting steeper. Alright, ħaniqafaw illum. Tajjeb, inkomplu minnaw il-darba li ġejja. Ok, nhar it-tlieta, u ġvera. Tinsewx li għandkom dak il-homework ukoll, pruvaw l-estuħ. Kemm jista' jkun malaj. L-aħħar domanda jiftit triki biex ngħidilkom il-verità. Infatti ma tajtix ħafna marki. Alright? Jiftit triki. Imma pruvaw aħsbu bil-metodi li għamilna tistgħu taħdmuha. Alright? Tistgħu taħdmuha. Imma tridu taħdmu ftit moħħkom. Alright? Ħallejtkom mela. Ciao ciao.